Good evening, everyone, and welcome to Further Mathematics webinar. It is the third one in the series, Further VC Mathematics series. My name is Bojana Graham, and I will be your host for tonight's webinar. So today we'll be looking at statistics and modeling linear associations. And before I introduce our presenters, I would like to quickly go through a few screens and admin stuff. So it is a live webinar, but you can ask questions and chat or respond to questions. We'll try to respond to questions posed by the presenters. You will receive at the end of the webinar the PD certificates of attendance as in a regular workshop. You will be shortly seeing the presenters' desktops. And if during webinar you have a question, you can actually ask a question using question and answer or chat, and you can send the question either to the host or to the presenters, and we'll try to respond to your question during the webinar or after the webinar. So ask the questions and we'll try to respond. There are various options with the sound, so usually it goes via computer, but there are also some other options which are explained if you want to go on the phone. And if you are switching applications temporarily, the Cisco showing down there is the one to go back to the webinar. Your feedback is very important to us, and towards the end you will be asked to actually fill in a short survey. So after the webinar, there will be an email with all the files and link to the webinar on demand and the files. So this is all admin stuff, and now I would like to introduce our presenters for tonight. We have Brian Lennon, who is the C-Cube instructor and mathematics teacher at the Victory Lutheran College, and he has taught mathematics for over 28 years in Victoria, and also taught physics, science, and engineering diploma at Wodonga TAFE. He was a curriculum consultant in New South Wales and now teaches at Victory Lutheran College. And our second presenter is Roger Wenda, and he is mathematics lecturer at the University of Melbourne and also T-Cube instructor. Roger, it's going automatically. Sorry, I just need to be in this mode. Roger taught at Footscray High School and Catholic schools in Melbourne, Adelaide, and in the U.S. And he was also a project officer for new technologies for teaching mathematics. So I hope you enjoyed today's webinar, and we start with Brian, please.
Fantastic. Thanks, Bojana. And I will just switch you across to my screen, which should be popping up at about now. And I'm just going to switch a camera on. Don't get too worried.
Yes, you can see your screen.
Yep. Because I know people tune into these webinars, they set themselves up make themselves comfortable, get a cup of coffee, which I've done. I've done that too. I've just got something in my coffee. I'll just take that out and just leave that there for a minute. I'm sorry, I'm just getting organised, you see, and I'm just going to move across here and just press that play button. And look, I'll get back to the main part of the story, because I've got a little PowerPoint which I'm using to start things off. And let's just play it. And, yeah, so Welcome to the webinar, as Bojina has already welcomed you. I think this linear association is just such a wonderful topic, and algebraic modelling in general, as far as I'm concerned, that's where it's really all happening. Having started life, actually it was a little earlier than 28 years ago for teaching, but yeah, initially as a science and physics teacher, when we can use mathematics to then describe what things are happening in the real world, as in a mathematics classroom, we talk about variables. We use variables in algebraic equations. We use variables in statistics. But of course, in the real world, a variable means some property of something real that is varying, that is changing. And if we take a look at some physical thing or things, and if we measure one changing thing about it, then we have collected univariate data. That's okay, but where it really becomes interesting in my mind is when we collect two or more pieces of information or pieces of data from each physical thing, and we have at the least bivariate data, and once we start looking for patterns and association between two variables within bivariate data, then we're talking and we're describing real things. I'm not alone in thinking this. Hang on, back on. I'm not alone in thinking this because there is such a huge emphasis placed on it in our curriculum, and particularly in our senior curriculum and VCE further mathematics course. The first thing I'm going to look at is what the study design says, and further down the track, you've possibly already guessed, I'm wanting to link it across to the current STEM phenomenon, and then we're going to look at fitting a line to a scatter plot. Now, even before teaching mathematics and before teaching science, as a student, I remember dragging out the ruler. We would collect data, draw it on the graph paper, drag out a ruler, try and play dot to dot with the points, or the so-called line of best fit. Then we have the algebraic model, and that's what I think is the most beautiful and elegant thing, because we're linking the mathematics to real world. Where do you get data? We will look at some considerations on that. Also some other useful tips and tricks, which things that you may or may not already know, but some time-saving little tricks that you can do with your TI-Nspire. We'll talk about saving time, some activities that are already made for you, ready to go, and where you can get more of those. But let's firstly take a look into the study design. I've lifted this from the 2016 design, and first of all, let's look at some of the changes in terminology, where we may have had dependent and independent variables in the past. We're now using this language, response and explanatory. So start using that language with your students, because that's the language that they're going to encounter in their exams. So the explanatory variable is that one that we previously called independent, the x-axis or the horizontal axis when we graph it. And the response variable, how a variable changes in response to the initial variable. So that's what we formerly called dependent, and we put that on the vertical axis. We not just look at things in a quantitative manner, but also qualitatively. So initially just drawing a scatter plot of data and being able to describe an association as, for a start, does it appear linear? Is it linear positive? Is it strongly linear positive? Is it strong, moderate, or weak? So that's sort of language to be used as well. And you see that in the study design. We look at, we look at Pearson's correlation coefficient. We look at also cause and effect. This was in the study design before. And then we look at fitting our model, and take a look at this. We've, since about year 9, probably had linear functions as y equals usually the x term first, or the variable term first, so y equals mx plus c, or plus b, depending which school you went to. But generally, in statistical terms, we put the independent term first. So it's worth pointing that out to students, because that's the way it will be presented to them in exams. When you do a model using the Nspire, you can actually do it either way. My suggestion would be to start moving across to this one, if you haven't already. This bit here, this is always a bit of fun. It's occasionally examined. How do we actually work out our A and B values for the regression model? How would you do it from first principles? You know you can work out means from first principles, and if you really want to go the full distance, you can even work out standard deviations from first principles. Of course, we know that when you're using your technology, you don't have to, but it's worth the I guess having students at least see how they can deal with that should they encounter an exam question on it. The whole idea of this least squares method, which is, why do we square? And I think Roger's going to talk to us more about that in his segment. The residual analysis is often also emphasised in the study designs and in the exams and examiners' reports, so take a look at that area. I will later on in tonight's webinar come back to, in the tips and tricks area, some clever little ideas for your A and B calculation. But let's get back to this STEM thing. I just think this is so good. The fact that if you're using TI-Nspire technology, you can actually plug in real-world probes, such as a temperature probe, light meters, pH meters, accelerometers, all sorts of interesting things. And of course, there's a whole heap of activities that are being written to support this area of study. What you see on the top right there, that's part of the apps for iPad, TI-Nspire apps for iPad, and that's something that's becoming quite popular. It's actually a Bluetooth connection between the probe and the iPad. It's your familiar TI-Nspire software, but it's graphing the data live as it's collected. STEM, of course, being something of great interest, pretty much right across the world, and you can see here a bit of an emphasis from our own government. Let's just switch back to my calculator at the moment. You saw my coffee, and back at the calculator. We've had a bit of a cooling curve there, as you can see. So this, has it gone up again? It could be. I closed the door. So we've had, over the time that I've just been waffling on, we've had some data collected, and I can even model this. And okay, it's not linear, but I could, if I was, I could chop this data. I could examine it, say, just from here to here. But this has been collected. You saw in the camera that I had the temperature probe from my coffee, and it's been plugged in through this link, and at the other end of this link, on the bit going out to your left, that's just a standard full-size USB plug that's gone into my computer, so that I read this on my computer software. The students doing this, they might want to use something like this, where the stainless steel temperature probe has at its end the mini USB plug. This one here, which attaches straight into their calculator. And so they can collect the data directly from that. A bit of fun also with these stainless steel ones. You get a few of these in the classroom. They instantly activate once you switch them into the calculator. So the data logging page will automatically open. And kids say, oh, the temperature, let's make the temperature go up, let's make it go down, stick it in your hand and under your arm and so forth. It's not long before, particularly so with a class of Year 10 boys, one of them will stick it in their mouth. And at that stage you say, oh, well, look, it should be reasonably clean, but the last time these were used with a class, they were used as rectal thermometers. And and the fun of that is that the boy who's done it is then halfway through asking what that actually means when he figures it out, and he starts spitting and spluttering, and yeah, so that's just a bit of fun that you might have. I can analyse my data within the data logging app. There are the data, and I can chop it and model it and so forth. But what you see, there's the one there for data logging. But what I can do is also export it back into a standard calculator page. I can put it into a list and spreadsheets page. So there it is. There's the run time. I did data collecting once a second, and I set it up for 5 minutes worth of data. So there they are. And so there's my data in 2 lists. And of course from there I can put it into a data and statistics page. Looks messy, but let's put time on the on our horizontal axis and temperature on the vertical, so our response variable. And I don't know that we really want to fit a linear model to that, but or what model you may wish to try to fit. But what do we do? How do we fit a model to these things? I'm going to switch you back to Roger to tell us how we can fit models.
Thank you, Brian, and waiting for Roger to see his screen and continue with modeling linear associations.
Good evening. Hoping that everyone can see my screen.
Still waiting? Yes, it's coming up now.
Okay, good evening, everyone. The problem that I'm going to show you today is one where instead of having hundreds of bits of data, we've only got 5. And the reason for that is because the screens start to get filled up a lot using the application that I'm going to be using. And the purpose of what we're going to be doing today is to model, try to replicate the old least squares regression where you use graph paper and do a by hand, slide the ruler and try to fit the data as was talked about earlier. And I'm going to show you how you can actually imitate that with the technology and develop the understanding in the students' minds about what the least squares regression is all about. And visual estimation is going to be a really important part of the feature of this file. This starts off as a 2-page file. I'll just show you how I originally created it by doing Control and then the Up key. It's 2 pages at the present time. You can see the first page is a notes page, the one that we had displayed earlier, which we'll go back to in a second. And the second one is the data and statistics, which I've already pre-entered just to make this fit into the required amount of time for us today. At the end of our presentation, this will be a 7-page problem, and you'll be able to find that completed problem if you wish on the TI site. We'll make it available to you, and you'll also be able to contact me if you wish and talk about it then. But we start off with this problem, which, if you can just read it through, is taking a look at pairs of data, just as Brian was talking about before, whereas this time the horizontal variable will be the diameter of a particular tree, And the response variable, the vertical one, will be height. So we're modeling height versus diameter. And the ultimate question we're going to try to answer, the questions are here on the notes page. What trunk diameter should coincide with a height of 15 meters? And you can see that they might want to start off by estimating, it's probably going to be somewhere between 14 and 18, but they don't know how these data look yet. So in order to get a picture of this, I created a list and spreadsheet page with just the 5 pairs of data. The 2 list variables, diameter and height, are used, and the numbers are listed in there already. We're going to now take a look at a data and statistics page. So I'll insert that using one of the different ways, data and statistics. As we said before, we're going to have the horizontal variable be the diameter of the trees, so there they are, and we'll have the height of the tree be vertical. Now, in setting up or creating this problem, I've done this with a particular idea in mind, that I wanted the points reasonably spread out so that as the graphics that I'm using in my explanation, from the teacher's point of view, as the graphics get more complex, the students can still see it. I'm going to actually make the screen just a little bit bigger, and the students have a better chance of seeing this down the back of the room, remembering that at any stage, the teacher has the choice of sending the file to the students to actually get them to work on it, and using the Navigator system, all that works quickly. But I'm looking at lots of pedagogical kinds of decisions that teachers are going to make in order to teach the actual concept. And the concept here is, what is least squares regression all about? Well, the first thing that we're going to do on this screen 1.3 is just to introduce the concept of a movable line. I go to the menu, Analyze, and item number 2, Movable Line. For those who have never used this before, it should be noted that the default position of the line is always at a 45-degree angle. It doesn't take any account of the varying scales on the 2 axes, but it's always at a vertical angle. And you have a couple of different ways to move that line. If you take the cursor towards what looks like the center of the line, you get the 4-pointed object there, and that allows you to move the line up and down, essentially maintaining the same gradient, and that can be useful. If you have your cursor at one of the other ends, you get this yin and yang curved arrow kind of approach, and that indicates that when you move that, you're able to adjust the pitch or the gradient or the slope, whichever word you're using to describe how the angle is pointed. Now, in the old sliding the line with a ruler days, we actually did that. We took the ruler and we tried to fit it so that the line was going to go somewhere in the middle. I'm noticing at this stage that the equation of the line, which is handy and dynamic and changing, but it's right in the way of all the points. So I'm going to flip it up here to the side. By the way, this is listed as a variable now. The M stands for movable. It's movable line 1, and it's a function of x. And you can see that the default for this is in the mx plus b, or the mx plus c mode, not in the usual statistics mode. It's just useful to point that out to students. Now, what we've done with students is usually ask them, well, how can I get this line to generally fit the data as closely as possible? Some students might say that what we have on the screen now is good enough, but others might remember that, well, a good thing to do is to try to get as many points on one side or the other. I deliberately chose 5 points so that we might have the line running through the middle of one of them and leave 2 on one side and 2 at the other. So by a succession of movements using the mouse, I've got the line, and I can place it up here. And at this stage, if I have a good data projector, I can call on individual students to say, could you advise which part of the line I should move? And someone might say, take the upper part and move it down a little bit, so I can do that. And as I do that, the lower part swings up. Anyway, I get it to a situation where I think, well, that looks like it fits the data reasonably well. Although I've only got I've got 3 points above the line and 2 points up. Maybe I want to have 2 and 2, and in getting that with this, that might be a bit trickier to do. I'm not going to spend a lot of time on it, but maybe about there looks reasonable to students, and that's fine. Students could record that at this stage, but it's going to be remembered as a variable, so I'm going to just leave that. I'm now going to introduce another data and statistics page. This time I'm going to do it using the home key, glide the mouse over the data and statistics icon, click on that, produce the same scatter plot where diameter is horizontal, height is vertical. I've got the same scatter plot with the same axes on there, but this time I'm going to introduce something different. First of all, a second movable line. So that's under Menu, Analyze, Add Movable Line. Notice this time it's a new one. The variable is named as M2. It's remembering M1 from the previous screen 1.3, and now I've got a new one. And I'm going to do different things with this. I'm going to add in the concept of residuals. So I go to the menu, Analyze, go down here to Residuals, and I'm going to show the residual plot, making sure that I do that first. There's a pedagogical reason for this. Now the teacher has a chance to say, well, one of the ways that we can numerically test whether we've got a good fitting line is to try to minimize how far each of these key points is from the line. Now, first of all, I might get up here and I might move the line a little bit so that the upper part of the screen, it might not be exactly the same as we had there with M1, but that doesn't matter. That's a pretty close fitting line. But when I go down here, I've got some really nice detail in the corresponding residual plot. Notice this point here. Its coordinates are 4, 3.23. The 4 relates to the fact that this point, which it's related to, also has a first coordinate or a diameter of 4 centimeters for that tree. But the 3.23 refers to the fact that that point is 3.23 units above its corresponding point on that black line. Now, in this particular view, we can't actually see the black line. I could adjust the axes if I wanted to. I didn't want to do that, but could adjust this set of axes to actually see it. But there's a distance of 3.23 above it. If I go to this point over here, 1413, which means a 14 centimeter diameter tree has a height of 13 meters. That was from the original data. Well, what I can see down here is that that point is 2.2 units below the line, the movable line that I've put up in the first diagram. And therefore, what I want to be doing, if I want to adjust the position of the movable line, is to just swing these around so that I can get these to be as close to the zero line as possible. And I'll do that a little bit, but I'm not going to spend a lot of time. Again, you could get students involved in a great amount of discussion about where it should be moved. And again, if the students are doing this as well as with you, then they might be coming up with their own results. And if you have the Navigator system, of course, you can watch that, make a student a presenter, and off you go. But you can be in control of this as much as possible. That's not a bad one. That's not a bad one. But a problem exists here because some of these residuals are positive, like 1.34 now, and some of them are negative. If we want to get an overall idea of balance, finding the average, for example, we know that the negative values are going to cancel out some of the positive values. We won't get an accurate reading. And this is why mathematicians have gone to that time-honored tradition of, well, make a negative positive for the time being. And a nice way to do that, other than using absolute value or modulus, is to square a number. And so we're going to introduce another data and statistics page. And that will be done here again, page 1.5 now. The usual scatter plot, diameter, height. And now this time on the menu, once again with the analyze, we'll add a movable line. You can see it's now movable line 3. Put the equation up there. Maybe jug it around a little bit here for starters. But then on the menu analyze, instead of in the regression going to, or instead of the residuals going for the residual plot, we're going to go for the residual squares. And the beautiful thing about this application in the Nspire environment is not only do you see the different squares and their sizes, but you also have an instant calculation of what the sum of those squares, which in geometry terms actually is, it's the sum of the areas. So currently those squares that are on here, from the biggest, which looks to be here, to the very smallest, which looks to be this little one in here, have an area of 17.17 square units when they're added up. Of course, when I adjust the line, I can get that to increase or decrease. And now that we can see a number, we don't have to worry about positions. We can grab the line, but we can pay attention to the number. And the focus can be on, well, how can we get that to be the smallest possible value? And students might, this is where the students would really benefit from each having the file, because through their fine-tuning, you might start handing out lollies if they get under 17, which we got here earlier. If it's really 23, you can watch them in real time on your Navigator software, bring it down here, and they can get a whole variety of values. I think I had it about 16 before. There's 17. 17. You can spend a lot of time. We don't have a lot of time tonight, so I'm about to wrap this one up. But let's say that the closest we got it was 17. Okay, so notice that I've done all of this and I've avoided using the word regression at all. We math teachers know, and the students will know it come exam time in November, that if they need to find the line of best fit, they'll just use brute force on the technology and they will get their line of best fit by just hitting the regression button, and they'll get it. But by having gone through this step by step and actually drip feeding them the information as they go through, a discussion can take place in much slower time than I've presented here in the last 20 minutes. But a discussion can take place about what it means, how to change things, why is that a better fit than this, etc., and really get them to engage with the data, which this technology enables you to do so much better than if you had students with sliding rulers on graph paper, and in general, only a few of them are probably doing the right thing at this stage. This time, with the technology, they can all stay engaged. Finally, what I would like to do is introduce a data and statistics page a calculator page, and go to the home key and introduce a calculator page where we now start to solve the question. You might remember the question asked us to find the diameter that would produce a height of 15. So we set up a series of situations where we're going to solve an equation, and the equation is to solve, well, let's take the first line. And if we look under variables, we've got a whole heap of them. And if we solve on the variable key, if we solve and we take the M1 line, we call that M1 of X. And let's say, well, let's see the value of X when M1, which is the movable line, which is actually representing the height of the trees, it's the old dependent variable, now the response variable, when that's equal to 15, we solve that for X. And we say that, well, you'd need a diameter of 13.14. That was on our first estimation. On our second estimation, we can do the same thing. Solve, open brackets, go to the menu, choose M2 of X, and have that equal to 15. And since we were using residuals, we're going to assume that that was probably a better estimation, and we get a slightly different answer because it was a slightly different equation. And on it goes. We'll finally go to the one where we use the residual squares, which is solve variable M3 of X equals 15. And remember, you're always doing this comma X because you're telling Nspire to solve it for X. And we get 13.3056. But what's the best one? Well, the best one will naturally be the regression equation that Nspire will be using, fitting all those rules that were explained in the study design. And so the regression equation, which can also be found in our variables once we do a stat analysis here. So let's go to the, go back to the menu and look at statistics and stat calculations for our variable, and we're going to look at the two variable statistics where the X list is the diameter, the Y list is the height, and we have all our information up here. And somewhere in here we have all of our two variable statistics. But as well, what we have in here, we have the ability to go to the menu and, sorry, we have to be back on the statistics page, so I'll press escape a couple of times. We'll go back to the data and statistics page, and under the menu, we'll go to the analyze, and this time regression item number 6, and we'll show linear. Now this is what Brian was referring to before. Let's put it in the A plus BX form, because that's what students are going to be looking for. And you notice that that's the actual, the one that's currently highlighted, the black one, is the actual true regression equation. The non-highlighted line was the one that I was fitting using the residual squares and trying to minimize that. So that's not a bad fit. But we all also notice on our calculator screen that we can finish things up and say, well, in the variables we now have the regression equation. The regression equation is this variable down here, and we can still solve that. The regression equation of X, set that equal to 15, solve it for X, and the best value is 12.97. So just a little bit under 13 centimeters answers that first question. We're getting a little bit further on to things there today, so I'll just summarize for you and now show you that what we have is we've developed now a 6-page graph where we had the original data and the problem, the lists and spreadsheets where the data was entered, and then the movable line that we just tried to fit it as best we could, the second movable line where we used the residual plot, the third movable line where we not only have the residual squares, but we also have the regression equation, and then the calculator page where we did all our calculations to answer the question. So a step-by-step approach there can make the teaching of the least squares regression something that has a lot more impact and hopefully some lasting knowledge for the students as to what the actual process is. Before I hand back, I just wanted to show the participants tonight a little bit about where data, a good place to find the data. Now, the data that I showed you just a couple minutes ago was data that I made up. But if you look at the Census at School site,
yeah, the kids love it because
the Census at School site, which is absolutely on the Australian Bureau of Statistics site, if you click on education, you notice a little blurb about the census at school. Unfortunately, the government saw fit in its cutbacks to conclude the project on the 18th of August 2014. But before they did that, they collected data from actual students in Australia, from prep to year 12, and these data sets on a range of questions are saved in Excel files. I'm just going to briefly show you how you go about doing that. So as we go into this in the Census at School, I click on that link. I go to the random sampler. I first of all have to agree to the terms and conditions, which I accept gratefully. And then I've got a whole series of parameters that I can put in. And just because we're getting a little bit short on time here, I'm just going to very quickly show you, without any reference to why I've actually chosen them. 2012 seemed to be a good year to get numerical data. The sample size that I'm choosing is 30. You can get anywhere up to 200, but it's all dependent on other parameters. They might not have enough data, and if it's more than 10% of the sample, then they'll ask you to change things a bit. I'm going to choose from all states and territories, and as far as year levels go, I'm going to choose year 12 because most of our students who do further mathematics are year 12 students. I'll ask for both males and females, and then I will get the data sample. Now in the data sample, I get a summary of what I have selected, but very importantly, I've got the list of the variables that were asked in that survey, which is a nice little PDF. And you can see they ask all sorts of very straightforward questions to kind of the funny ones. I love the belly button one, which is question number 10. Students would have a great deal of fun answering that one. But
the other one, of course, was the Excel file there.
That's right, the Excel files, and I'm going to go.
Which you can quite literally just drag and drop into
back
your
to that.
calculator.
That's right. So, and the Excel files, which have all the data down there that you would need, opening with Microsoft Excel, and here it comes. So it's very easy, and with Nspire being so easy, where you can just copy a column of data and then dump that into a listen spreadsheet. So that is very, very useful. Finally, just minimize that. Also at Census at School, you have data for calculators, and I'm just pointing this out as something where you can get the data in Excel files. You can also get them in terms of TNS files. So the Australian Bureau of Statistics site is one of many places, but it's just so handy. It's all there. I really urge people to go about doing that. Well, thanks very much for listening, everyone, and I'm going to now hand things back to Brian.
Thank you, Roger, and we're waiting for Brian?
Yeah, look, I'm in trouble here because my coffee's frozen. And you think I'm joking. I'll show you. We'll go get along to the useful tips and tricks. But what I did, Roger, while you're chatting there, I grabbed the data and I selectively struck some of the data. You may recall that the picture we had, move to our picture, hang on, back to, sorry, our picture for the graph, that we had what seemed to be reasonably linear cooling for about the first half minute, and then she leveled out to room temperature and even bumped up a little bit. So what I've done is I thought, well, it was cooling out of what seemed to be a roughly linear rate, and I listened to Roger explain how I can model this. So what I've done is I've just looked at it for the first, I think, 34 seconds or thereabouts, and there we go. And the data beyond that has been struck, as you just saw on this. If I look at the data list in the software itself, from 35 seconds onwards, she's struck out. So I then created a little graph, and here's the model. So it's, yeah, she's still curved, but I put a linear model on, following Roger's advice, and I can see that, okay, I was a little bit slow getting to my cup of coffee, but when I did start looking at it, it was about 41 degrees Celsius initially, and then it started to reduce temperature at the rate of about 1/3 degree Celsius per second. And what's interesting about that, once the regression has been done, this stores in the calculator as an equation. I'll show you what I mean. If I now open up a calculator page and look at my variables list, I can see that stat regression equation is one such thing. And if you see the brackets there, it's asking me, well, let's plug something into your stat regression equation. I'm going to plug in 0. And there's the initial temperature of my cup of coffee. If I rerun that and put in, say, 34, then we get to see what it looked like after that 34 seconds. And I can have a bit of a go, say, halfway through that, run up the equation, and at, shall we say, 17 seconds, it was about 36 degrees. And I can actually go back to the original data and check on that. And there we go. Yeah, not too far out. And you saw in the study design that we were talking about reliability of interpolation and extrapolation. And the extrapolation is where I have a bit of difficulty, because what's now happened, it's been, where are we, 150, shall we, hang on, what have we done? Yeah, it's probably been about, it's already about 3,000 seconds since we started this experiment. So if I put that in there, you can see my problem. So the coffee has not only cooled, it's not only frozen, it's frozen well beyond absolute 0. So it's colder than anything in the universe. And so I'm having a bit of trouble with my coffee. Or it could be that maybe my statistical model, linear in this case, has broken down and doesn't work as well for those times. I can also do interesting things, like exactly when did the thing freeze according to that model. So I can solve the statistical regression equation for x equaling 0 for x. So this will tell me when the thing got too cold. And it happened at 128 seconds, which is what's only a few minutes into the deal, isn't it? Yeah, so where are we? 2.1 minutes in, and the thing's frozen. So that can sort of be part of the dangers of looking at just a small amount of data. You saw earlier that there was much more data that I had from that experiment. And talking about much more stuff, there's still heaps more I'd like to show you. Mindful of time though. Useful tips and tricks. Previous webinars are available on demand. And now I noticed in the participant list that we've got Russell Brown online. He's done some great stuff on this. Teamed up with Rodney Anderson about a year ago. Did a webinar, and it's still available, Statistics with TI-Nspire. And this is part of the documentation that, that Russell prepared. And you see here reference to the Australian Bureau of Statistics Random Sampler. Wonderful, wonderful resource. And also I've used it with students in SACS. I've used it in further math SACS because they get different, because of that random sampler, they get different data sets. So you can quite confidently know that students are crunching their own data because they have to come up with unique solutions just to their data set. Russell teamed up with Trevor Redmond to specifically look at a webinar on STEM. I haven't hyperlinked that into my PowerPoint, but I have a third one that I did myself with Russell September last year, and there's some clever stuff in there too. This document, once again, Russell prepared, and he put in, see the little calculator icon? Through the discussion, if you click on that icon, it opens up. He's hyperlinked it to a TNS page. Now, let's have a look at this. Remember I promised you before that we would revisit the calculation of A and B for the regression model. Let's have a look and see what happens. It's warning me it's going to open my calculator. I'm happy enough with that. And I get instructions within the calculator file. And if you haven't yet played with dynamic notes, I recommend you do because they're great. Once again, just on the home screen here, everyone knows the calculator page. We all know the graphing, the geometry, the list of statistics, the data. This one here, the notes, and I also showed you earlier, the data logging page. But on the notes page, let's say that my correlation coefficient wasn't 0.765, but let's say it was, I don't know, let's go with just 0.6. So I've edited in the blue space there, press enter to confirm. It comes back at me in green telling me that. Let's say that the standard deviation from my first list was, okay, let's go with 1.2. You've got the idea. So it modifies. Let's say that the mean of the X list was, I don't know, what's a number? 56. Sounds good. And let's say for the Y list, I'll think of another number, 78. And straight away, the calculations have been done for me down here, below these lines. So it adjusted. Let's change that 78. I'll prove it to you. Let's change that to, I don't know, a 24. See what's happened? So it's changed our A and B values. Or our A value there anyway. So I think that is very, very useful. It's available to you. After this webinar, you will get a copy of this PowerPoint. And when you play it, if you click on these, it will take you to those documents because I'll put it all in one zip file for you. And formulas in dynamic notes, well, we've just been playing with that, haven't we? So you know how to do that. Statistical results is another lovely little shortcut type thing. Let's have a bit of a look. And I actually opened this before. Yes, here we have a set of data. So it's univariate at this stage. That's all we've got. And what Russell prepared was on a notes page that there's the full statistics summary of those data. Of course, I can do it on this page by just typing it in. But I can, and there it is, so the mean is 110.58. There we are here. But of course I can also do it on a notes page, not a notes page, just a standard calculator page, because once those statistics have been calculated, the calculator knows them as variables. So for example, if I want to know how many data points there were, there it is, there were 12. If I want to know the mean, it's down here, there it is. If I want to know the whole box and dice, I can just ask for stat results, and there they are. So that's just another little time saver. Think of students in exams. And talking about exams, here's another one. Only 2 points are needed for a linear equation. And here, again, credit to Russell. You see on the right here the very familiar formula of the gradient between 2 points, and below that, using that gradient in the point gradient formula to work out the equation of a line. So a question in this particular instance was talking about transformed data, and it was multiple choice. So data are transformed, which is the best model that fits that. Now, sure, you could type in the data into your lists and spreadsheets, you could do your regressions and your transformations and so forth, but you only need 2 points for a straight line. So let's take the point, 111 and 2582, and put that into your calculator. And I did this before. And there they are. Bang, 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 hit go. There's your equation. So what I've got, y equals 3x plus 8. But back in our document, sorry, not that one. Back in this one, there's really only one contender. Of course, it's 3x squared in the actual equation because of the transformation. So time saving in that rather than doing all the data. Coming back into this, and we're about done. More activities, more PD, I'll just point you towards. Senior Curriculum Inspired is opening up. When you click this on your PowerPoint, it will take you to that new part of the Texas Instruments web page. You can click on, say, Further Mathematics. You can see activities that can be downloaded, Hit the Brakes, Charles, and more. There are also activities, and including ready-made tests on the earlier part, Australian Curriculum Inspired, and also more activities. Here's a cute one, Monopoly. Have you ever noticed playing Monopoly that from go you get all the cheap rubbish in the first street, and then it sort of increases as you go around, and on the home straight we're getting up to Mayfair and Park Lane and so forth. And could we perhaps see, is there a relationship between the number of places out from go versus the cost of the property? Well, we can do that, can't we? It's just a matter of collecting the data, and let's now have a look. Spaces out from go, and the cost. And there's certainly a pattern. We have some anomalies here, and Roger, what do you think these might be? Maybe ask people to type it into the chat window. So 5 spaces in, there's a property for $200. 15 spaces in, a property for $200. For $200, for $200. Yes, those of you who've typed it into the chat space and said railway stations, you are correct. And $150 here and $150 here are the 2 utilities. I could put a model to that, or I could strike data, as I showed you earlier, and here's one I prepared earlier. So I struck out the railways, and I struck out the utilities, and there's our model. And as Roger showed you before, we can also get the hang on, analyze. We can also take a look at our residuals. this is Old Kent Road, first up. It's overpriced. So you can see across here, anything above the line is too expensive, and below is, yeah, it's a bargain. Buy it up. You might think that sounds frivolous. Peter Fox suggested an idea to me that actually you could do that to analyse property. If you are in a particular suburb in Melbourne, have you noticed that the prices change depending on distance from the CBD? Draw a line between your place and the CBD. Take a look at the suburbs it goes through, or the areas that line goes through. Take a look in the weekend paper, work out the median price for homes in those areas, and see whether you're above or below. You can graph that. It actually is linear. Bojina, we're about at time. There's more available.
Thank you very much.
But I'll let Bojina tell you all about that.
Thank you very much, Brian and Roger, for a very informative and at times exciting webinar with lots of ideas and activities teachers can take to their classrooms, and also from pointing out where the data can be found on various websites. And also it was quite interesting to see different approaches at looking at linear regression and residuals and how those can be accessed. So as we said, we have Australian curriculum inspired with lots of activities which can be found there, both for students and teachers, and there is a few things here as well. We have also past YouTube videos with exam tips. We have some upcoming Learn, Energize, Connect workshops, one in Geelong on March the 30th, one in Melton also on the March 30th. And you can subscribe to the newsletter. And the next webinar, which I would like to advertise, is happening on Wednesday, March the 9th, and the presenters will be Ray Cross and Rodney Anderson. And if we go to webinars page, so that's what you can find on Australian New Zealand website, we see the webinars here, both upcoming and on demand. So I would like to remind everyone to complete the feedback survey at the conclusion of the webinar, and everyone will receive a follow-up email within about 48 hours with all the files available. And thank you again very much, Brian and Roger, for a very, very good webinar with all those helpful ideas.
You're so welcome.
And yes, thank you. And good night, everyone.
Good night.
Thank you. Good night. I'll get back to that coffee.